Okay, so dear colleagues, hello everyone. So today is our microwave seminar. And today's speaker is Dr. Takuya Sasatani from the Tokyo University. He'll be talking about the wireless power transfer. So Taku, please, you can start.
Okay, thank you for inviting me for this talk. I'm Takuya Sasatani from the University of Tokyo, and I'm a researcher working on projects in the interdisciplinary field of computer science and electrical engineering. And today in this seminar, I'd like to introduce some of my recent work towards enabling ubiquitous wireless power transfer. So here's the outline of the talk. First, I'm going to talk about the ubiquitous wireless power transfer we envision and the confronting challenge towards there. And then I'm going to talk about two projects we recently worked on. The first one is a project for making the deployment of 2D wireless charging systems easy by integrating the concept developed in computer science community. And this work was published in ACM IMO, a top journal in the ubiquitous computing field. And the second topic is going to be about a room scale wireless power transfer system inspired by cavity structures that enables efficient power delivery throughout the entire room volume. And this work was published in Nature Electronics about 2 months ago. And after these two topics, I'm going to summarize and conclude my talk. So to start with the intro, basically, I think most people here have seen these wireless charging pads before. They're installed in like new iPhones and everything. And if you put devices on the pad, it gets charged. But like these work pretty well. But we thought this could this doesn't really change how we interact with electronics. So we want to make it more ubiquitous and enable an experience that electronics get charged through natural daily interactions. So that's what we wanted to do. And through this advancement, we're hoping that we could power devices, mobile devices in living spaces, and also empower physical computing systems in industrial spaces. And of course, a lot of people want to do this. So there's a lot of challenges here. And one critical challenge here is that there's a trade-off between the power level and the covered range. So most wireless power transfer systems have a trade-off here. So raising typical approaches, one approach is inductive approach that uses coils to generate a magnetic field and receive it through electromagnetic induction. And another way presented by MIT in 2007 is called magnetic resonance coupling. So it adds the resonance conditions to these coupled coils, which kind of mitigates the orientation, which gives a bit freedom in positions. And these approaches use magnetic fields, and generally magnetic fields interact less with human biological tissue and human body. So because of that, we can deliver lots of power using these approaches. But on the other hand, it's hard to deliver power within long distances because magnetic fields decay quickly with increasing distance. So these approaches can deliver a lot of power, but still it can't reach far away places. And on the other hand, there's a lot of approaches that use electromagnetic radiation, such as microwaves and laser, and these can reach longer ranges. But the problem is that these systems interact a lot with humans' body and biological tissue and everyday objects. So if we can't deliver a lot of amounts of power because there's interaction there, and if you send a lot of power using this approach, the system will not be safe. So apparently there's a trade-off between power and range, and this is how we view the big picture of wireless power in these areas. And but the problem is that what we probably all want is, well, the most game-changing part should be delivering several watts of power, which can drive many mobile devices, which suffer from battery shortage, and in a wide range. So we thought if we could do something that reaches here, it would be a big contribution to the field. And I think a lot of people want to do this. So there's many attempts that try to reach this area from microwave lasers, but Our intent, our approach, our studies are basically focusing on how can we extend these potentially safe magnetic field-based methods to like wide ranges. So, and that's what we're trying to do. And so I'm going to talk a bit about this magnetic resonance coupling-based wire type transfer a bit. And I'm going to start from how the efficiency of such systems is determined and why it's hard to extend range. So this is the most primitive, one of the most primitive forms of magnetic resonance coupling-based wire charging system. So there's a power source and a transmitting resonator, which is composed of a coil and a coil that generates magnetic fields and a capacitor that tunes the resonant frequency of the resonator, and also the receiving resonator here, and a rectifier that changes this AC energy to RF energy to DC energy, and finally it goes to the load. So in practice, there's going to be a lot more components, but this is one most simplest model to think about. And thinking about how efficiency is determined in these kind of systems, there's two important parameters. So one parameter is coupling coefficient. I know applied physics people will use stuff like coupling rate, but I'm going to stick with magnetic coupling coefficient here because I'm an electrical engineer. Like it's basically the proportion of transmitter flux that penetrates the receiver side. And another parameter that determines efficiency is a quantum factor of these two resonators. So this is in general confined energy per loss in one cycle of oscillation for general oscillators. But for these kind of electrical engineering systems, it can also be defined as like the angular frequency times inductance over resistance. So and using these two parameters, the power transfer efficiency between the transmitter coil and the receiver coil, the AC to AC efficiency can be determined like this. And the important part is that this can be simplified using a KQ product. This is a function of KQ product like this. And well, long story short, if the KQ product is high, the efficiency is high. And that's how that's how the basis of these systems work. And with this insights, looking in how this KQ product changes within like different physical implementations, like thinking of K, the coupling coefficient. If the transmitter coil and the receiver coil is quite close, the resonators are placed nearby, and also the size is not so different. Most of the flux that gets out of here gets into the receiver, so that gives a high K. But on the other hand, if the distance gets further, like that's 100 degrees, and also when the system is asymmetric, so a large transmitter and a small receiver, it also gives a decrease in K. And when this both happens, it's going to be horrible. But on the other hand, that's what we really need for ubiquitous wire type transfer. That's why it's hard. So like if you want to do a wire power transfer in a wide range, it's usually the K is coupling coefficient is going to go low, so it's quite hard to do efficient power delivery. And and some may think that it's a KQ product. So if we can't increase K, we can. Some people might think that you can just increase Q. But for enhancing this, one approach is to use low loss materials and also tune the structure of the coils. So like this famous structure is called helix coils and spiral coils, and like tune the number of turns and pitches. And there's a lot of ways to optimize the Q factor here. But our perspective is that there's not so much room for improving these the quality factor or these typical coils. So so we're working on different ways to do powering small devices wide ranges, and so that can be translated into maintaining KQ product in a wide range. And one way we're working on is using transmitter arrays, so not covering the entire volume, entire space with one transmitter, but using multiple transmitter to cover the space, so you can split these into grids. So and that enhances the coupling coefficient here. And well, a lot of people, we know that a lot of people have been working on these kind of stuff for more than 10 years. Like as researchers working also in electromagnetics and also in interactive technology, we still thought that like there was a missing piece about how to deploy these surfaces. So we're working on system level technologies and to facilitate the deployment of such systems. And another approach we're working on is making new types of transmitters that also enable that not coil based and makes a new enhances the efficiency by introducing new types of resonators. So I'm going to introduce a piece of research for each approach in the following sections. So the first one is going to be about 2D wireless charging. And thinking of these, so this research question of this part starts from like how can we naturally power these devices through native interactions. And through thinking about this, we notice well, obviously, most of these devices are placed on surfaces in living spaces, such as the floor and the desks and shelf boards and walls and those stuff. So well, we thought that augmenting these surfaces in living spaces and charging surface would be a kind of natural way, rational way to make this happen. So, and the next question that arose for us was like how to augment these surfaces. So a kind of typical way to make wireless charging surfaces is to pack a lot of transmitters onto the surface and wire them independently. But we thought there was a missing viewpoint into how and who builds these surfaces, and because like the current charging surfaces require custom design by RF engineers and electronic experts in electronics to cover each product. So we'll need to like hire skilled electronic engineers in addition to furniture designers to make a wireless charging desk, which is not really cost efficient. So we thought we can solve this problem by enabling the general public to make these kind of systems by themselves. And for this, one commercial model we got inspired from was like these tile carpets. So if the users want to build a really lay carpets in a large room, they can make an order made. They can do an expensive order made thing, but they can also just buy a lot of panels and place them by themselves. And this made us wonder if we can make wireless charging systems in the same way, so the users just buy ready-made panels and just place it on the surface to augment it. And this is what we got from this concept. I'm going to talk about how it works laterwards, but the users just buy a bunch of these tiles and to connect one of them to the outlet and just lay them without connecting them. And so, wait a minute for setting up. Yeah, and so just by doing this, this makes this wireless charging surface. So if the receiver comes on this and that needs power comes on here, power is directed on the surface through these modules to the receiver. And if the position of the receiver
Takuya, we can't hear you right now.
Sorry for the inconvenience. Can you hear me now?
Yes, yes.
Okay, from where did I stop? Sorry for this.
So from the next slide, probably. So this is what we heard.
Okay, so yeah. And using this system, like thank you so much. And we're envisioning usage scenarios such as the users just lay these ready-made modules on the back of their own shells and make a wireless charging wireless charging shelf by augmenting them. And the next part is how this works. How this works. And it's basically based on a well-known phenomenon called multi-hop wireless power transfer. Probably it's similar to like metasurfaces that's probably the applied physics community is familiar with. But basically, when the supposed receiver is placed far from the transmitter, usually when using magnetic field, you don't get so much power in this configuration. But if you place passive relay resonators that can pass down power, you can make the system to kind of, if you put like coupled oscillators in a line, you can make the power propagate to these relay modules, so the range can be extended. And the point we like for this approach, this thing, is that this multi-hop effect can be turned on and off at each module by a switch. So our idea was like packing these modules onto a surface, and by controlling the multi-hop effect at each relay module, power can be dynamically delivered to anywhere on the surface. So we can make a programmable powering route. And there was a big gap between this concept and making a real system. So there was a lot of engineering in this part, and we ended up making a hardware implementation like this. And there's 3 types of resonator modules in this system. So like there's a transmitter module, which outputs energy and control other modules with Bluetooth, and a relay module, the other hexagonal module is placed here, and also the receiver that receives energy from the system and charges the connected devices. And this is implemented modules. And the transmitter and relay and receiver share the same hardware, but just have different firmware to be configured differently. And these modules are equipped with a control board with microcontrollers, Bluetooth modules, and battery. And we also know that this battery on these modules can be charged via the wireless charging system, and we actually did that. So yeah, this is the one thing we developed. And the next part is how this system, the workflow of the system. And as you can imagine, like if we think about the users, the system has so much degrees of freedom, because the users can just randomly shuffle the board, or the users may, the receiver may be randomly moved, or the users may just place metallic objects that shields the magnetic field, that work at obstructive magnetic field. So we need to define a complex workflow that's kind of impossible to present in this time frame. So I'll just go over the essential point here, and please refer to the paper for the details. So this process starts from making a map of the resonators. So the users lay these lots of modules, and it kind of generates a direction graph based on adjacency using a proximity detection method based on inductive coupling. And then when the receiver comes, it sends out the signal, and there's also proximity detection here based on inductive coupling. And then the route from the transmitter to the receiver is computed. Then after making the route, the system checks if there's any obstacle on the route, or if this module still exists, if the users if they're preventing stuff like users just randomly remove that panel, and you can use that, and this system will go back to the routing process again. And finally, when it finds out the route is still valid, it starts sending power. And yeah, this is the brief workflow. I'm gonna show a bit several demo clips to demonstrate each process. So for resonator map generation, first this system is configured in a line shape, and if the users want to use it in a different shape, so this random shape, they can just shuffle it, and the system regenerates the map of these resonator modules, and that way the system can be reconfigured in a different way. And another part I want to show is the route validation process. It's pretty nice because if there's obstacle and a copper sheet on these panels, it stops the wireless power transfer. So if this happens, if this system detects that happen and it regenerates the root, and that so this can be also applied to a lot of other scenarios. Like if you want to send a lot of power, but like kind of want to avoid human, that's another thing this can do. And so yeah, so these kind of system workflow was defined, and like yeah, and this is about the system workflow. And next part, I'm going to talk about a bit of valuations, and we ran a ton of valuations because this was a systems paper, but just going to present the power efficiency measurement here. And please refer to the paper for the rest. So so I'm going to talk about the number of hops or distance versus transfer efficiency. And obviously the efficiency goes down as hops increase, but it's shown that 10 hops can be done with like 40% efficiency. And since the root of Alvus is reconfigurable, this means that the single transmitter can cover like a 20 square meter area, which is quite wide. And we also can just increase the number of transmitters, like putting one in each corner of the room to probably like further expand this area. So yeah, that's what we got for this project. And to summarize, we built a new system to facilitate the deployment of a 2D wireless charging system using multi-hop effect. And made new system design techniques for handling various operation scenarios, and found out that we can cover like about 20 square meter area using single transmitter. And we're still actively working on the project and doing some follow-up work. So the routing process I showed in the videos were kind of like a line, but we're exploring ways to make this a surface route to make it more efficient. And also we're making new types of protocols to maybe be able to integrate multiple transmitters in a single system. So yeah, that's the kind of stuff we're working on now. And that's about the 2D wireless charging system of this section. And the next part is going to be the 3D wireless power transfer inspired by cavity structures. And for this part, I'm going to start from the related work. And I believe a lot of people have heard about cavity resonance. And well, this is basically a metallic enclosure. And if a tone is input matching the room's the enclosure's resonant frequency, it generates standing waves that electromagnetic standing waves of electromagnetic field that makes a 3D distribution within the volume. And some research, some studies like this 3D nature of the field, and like try to do wireless power transfer in 3D volumes using this well-known cavity resonator. And this went well to some extent, but there was several drawbacks. One of them was that the resonant frequency is like strictly determined by system dimensions. So one problem is that these kind of transmitters work based on standing waves. So the operating wavelengths and the cavity structure dimensions have to be in a particular relationship to make it resonate. So imagine like there's two rooms with different sizes, and in that case, the two rooms will have different operating frequencies, and that's a big problem in the regulatory perspective, and also you need engineering perspective as well. And another thing is like if in these kind of electromagnetic resonance, you need an electric field and magnetic field to exist somewhere and going back and forth. But in these systems, both the electric field and magnetic field are exposed in the charging volume, so the space where people get in. And the problem here is that electric field kind of significantly interacts with biological tissue. So if people get in, you can't safely deliver large amounts of power. And also, like if there's a lot of daily objects stuff in this volume, the system also gets interrupted. And to overcome these drawbacks, one approach presented in 2017 is called quasistatic cavity resonance. So it's really similar to the cavity resonator, but the difference is that in addition to metallic enclosure, they have a conductive pole in the middle of the room here, and also have lump capacitors inserted here. And when these the resonant mode of this structure is excited, the current goes through the pole and through the ceiling, the wall, and floor. and with a capacitor inserted here, and a magnetic field is generated within the room volume. So it kind of works like it's similar to a cavity resonator, but it's made to work like a magnetic resonance coupling or like LC resonator system. And the advantages of this approach is like one thing is that the resonant frequency can be easily tuned by using these lumped capacitors here, because it's basically an LC resonator. And another thing is like the channel is mostly built with so the electric field is confined within the capacitors, and mostly only the magnetic field is generated per medium the volume. So even if people get in, it barely interacts with human, and also like even if you put a lot of furniture, it doesn't really affect the system. So it kind of makes an kind of ideal kind of channel within the living space. That's the good point of this. And to show a demo here, when this room resonates, the current coasters pull around the room, and the magnetic field swirls around the center of the room. And by using resonant coils, receiver coils that couple to this field generated by the room, it can deliver power within 3D volumes. So that's the good part of this approach. But there are still critical challenges here. And for example, like only like the magnetic field distribution of this approach was like kind of focused in the center, kind of non-uniform. So so around the center of the room, you can get a lot of power. You can deliver power efficiently. So this is the top view of the magnetic field up here on generated within the room. And also another drawback is that you always need a central conductive pole, which is sometimes annoying in some applications. And the study I'm going to present in this chapter is going to aims to resolve these two challenges. And that's the study. Yeah, I'm going to introduce that study now. And I'm starting from the basics. The coils on current uses current on wires, and that couldn't really extend so much. That couldn't give so much of a range of power delivery. And the QSGR, the quasistatic cavity resonance that I just introduced, used the cavity structures, and not just wires, but just made use of surface conductors surrounded volume, and that kind of worked as a key to make a 3D magnetic field. But still, it had some parts of the volume showed low efficiency. To be specific, near the walls of the room, the efficiency was quite low. And compared to these approaches, the idea here, proposed here, was that because we have a conductive surface that accommodates currents, it can also like widely distribute, but it can also, we thought that we can also make it flow in different directions, so make a multimode kind of structure. And so in that way, we can, even if you can't cover the entire room with one magnetic field pattern, we thought we could cover it by generating multiple magnetic field patterns. And so this is the basic concept, and from here is how we made this happen. And in the analysis part, basically the magnetic field gets generated near where the current is. So we try to think about a current distribution that flows near the edges of the room and the center of the room. So the blue arrows show the current distribution. So, and we ended up with this figures current distribution. The blue arrows show the current distribution near the edges, and the red arrow shows the current distribution near the center. And next, based on this insight, we thought of how to design these current paths by placing metal sheets and inserted capacitors in the right place. And we ended up in this structure that covers this range of power this range in power delivery. And getting a bit more into details, we designed we made this structure have two modes. The first one is called pole dependent mode. I mean that way because it happens only if the pole is here. And this is a top view of the current on walls in the pole. And in this mode, there's the current flows through the central pole. and goes back through all the walls. So all the walls have the same current in the same direction. And this generates a magnetic field that's strong in the center of the room and gets weaker near the edges of the room. So this resembles the original quasistatic cavity resonance work. And the key point of this work is that we added another pole independent mode. I named this pole independent because this mode occurs even if the pole is present or not in the same way. And this is the top view of the current. So the point here is that we want the current to focus near the walls. So we wanted the current to conclude in the walls. So we made the adjacent walls return paths of each other. So make the current flow like this, and so that's what we did, and then ended up in a magnetic field distribution, 3D magnetic field distribution, such like this, stronger near the walls. And we also did some kind of did a lot of analysis to tune these two resonant frequencies and independently to an intended value. But I'm not going to talk about that here, so please refer to the paper for that. And using these two resonance modes that can be allocated to the frequency we want, one way to use these frequencies, use these resonant modes, is to use both modes together. So selectively generating both. So if the receiver is closer to the center of the room, we can use this part. And if it's closer to the edges of the room, we can use this this PI pole independent mode that shows a stronger field distribution near the edges of the room. And that's when we can put a pole and we want to cover the entire room. And another alternative operation we could think of is that when we really don't want a pole in the middle of the room, like suppose in living spaces, we don't want poles there. And even in that case, we showed that we can using this field distribution, we can cover a fairly large range within the room. And yeah, and this is the analysis part, and it looked pretty much good in the analysis. So we decided to actually make this. We actually built this in Tokyo like 2 years ago, and dismantled it last month because we had to give the last space to other research groups. But this is what we made. So we made a 3-meter prototype test room. And based on the largest lab space we could get, using an aluminum frame and aluminum sheets and other like standard building material. And so this is the building process, and these are resonators. So we got Q factors of like 1,200 and 600, and these were not bad, but like there was a certain degradation from the simulation results, but it was pretty good. And also we could show that we could get the resonance frequencies to the values we intended. So so it turned out it's going to work well until here. And this is the resonance structure we got here, and this is abstracted system diagram here. And basically how it works, first the RF powers the input via the drive coil. So there's a signal generator and input and an RF amplifier, and that goes in the drive coil, which is coupled to the room, inductively coupled to the room, and the input frequency determines the excited resonant mode here. And then the room resonator oscillates based on the input tone. And when it resonates, the electric field is confined within the lumped capacitors placed on the walls and in the middle of the pole. It's hard to see it here, but yeah, in the lumped capacitors. And so it doesn't, so it confines most of the electrical field, so it doesn't interact so much with daily objects or biological tissue. And meanwhile, the magnetic field basically is dominant within volume. So this is kind of the ideal channel we wanted. So the dot wires, the magnetic field permeating volume and the electrical field confined somewhere that people can't get in. And finally, using this magnetic field, picking up this magnetic field, but using receivers, we can achieve power delivery from this RF amplifier to the receivers placed within room volume. So that's basically how this system works. And we did some evaluations of power transfer efficiency here. So using the first, we did we evaluate the dual mode operation using two modes together. So the two modes shows high efficiency in different areas of the room. So this is the mode that covers near the wall edges of the room, and this is a mode that covers the room center. And they still have that zone when used alone, but when used together, it showed that you can get high efficiency anywhere in the room. And being more quantitative, it achieved high efficiency over the full volume. And the part we liked is that this was achieved in a really asymmetric situation. So the transmitter was a room scale, and receiver was a mobile device size, about like 5,000. The ratio was like a few 100,000 to 1, which is quite asymmetric. And the strength of this approach is that we achieved high efficiency in such asymmetric conditions. And also we investigated the use of the PI mode, which we can operate without the pole. And this also delivered like, this had a dead zone in the middle of the room, but could achieve like 47% efficiency over the volume without the central pole. And this was also achieved with the small receiver in large rooms. So we were happy about these results. And to briefly compare these results with the original quasistatic cavity resonator developed by Disney and the Multimode QSR developed by presented in this talk, based on 3 metrics. So interaction with dielectrics, and with whether it covers the full volume and whether it needs a pole in the middle of the room. The original quasistatic cavity resonator had good properties in terms of interaction with the dielectrics, but could only had places where power delivery is inefficient and needed a conductive pole in the middle of a room in any kind of operation. And on the other hand, if the dual mode operation used developed in R and this work could cover the entire volume by using the multiple modes generated, and also in addition, like by using only the mode that doesn't require the central pole, so it can remove the pole while achieving power delivery in a fairly large range. So yeah, these are the results compared to the previous approach, and yeah, we saw improvement here, so that's good. And next part I'm going to talk about is safety. We conducted some basic safety analysis based on SAR, and in this frequency bands, tissue heating is a dominant health effect that happened, and SAR is called specific absorption rate, and it's a metric that evaluates the power absorbed by a unit weight of tissue. So, in a nutshell, like how much it heats up human body, how much heat it delivers to the human body, humans present inside the room volume. And in the simulation environment, we use an anatomical body model with all the electromagnetic properties annotated to each tissue, and move this human model around the room while transferring power and changing the power level of power transmission while observing the SAR. And as a result, we showed this primitive evaluation showed that we could deliver over 50 watts while complying with safety guidelines, IEEE and like ICNIRP, and those safety guidelines also used for evaluating cell phones. So yeah, and like 50 watts is pretty much good. So we can do a lot with that amount of energy. So this result, we also like this kind of result. And finally, I'm going to demonstrate, I'll show a demonstration clip about this technology. So now the room is on, and it's generating a 3D magnetic field within the volume, and it's delivering power to the coil I have in hand, powering the wirelessly powered LED. And because this system uses magnetic field, the magnetic field is dominant, I can get in without getting harmed, and we can also furnish the room, and the system doesn't get affected. And how it works, and this kind of review was a prior talk, but like, so a tone matching the resonant frequency of the room scale resonator is input to the room via this drive coil, which is inductively coupled to the room. And the resonant mode matching the input frequency gets excited, and the current flows through the walls, and that generates the magnetic field that permeates the volume. And when the room turns on, the magnetic field gets generated and delivers power to these small home appliances that have coils with them. So we show some examples such as light bulbs. So like we can put light bulbs like anywhere without caring about wires. And we also showed that we can power smartphones in our hands. And also like we showed that we can power like random home appliances that usually the cables turn out to be annoying. And the good point for this technology is that as you can see, it's pretty much looking like an ordinary room. And like the good point of this approach that we can make stuff wireless without negatively changing our life so much. And yeah, that's the qualitative difference from contribution of this work. And finally, I'm going to talk a bit about limitations. So there's still some limitations, and one of them is kind of common, same for all magnetic resonance coupling methods, but there's an orientation dependency. So there's a magnetic field flowing within volume, and the receiver needs to be normal to that to receive as much power. And if it's perpendicular to the field, it barely receives any power. And also, as a related limitation, when the receiver size gets smaller, the amount of magnetic flux it can capture also gets smaller. So that's also going to lead to lower efficiency. So we're kind of looking for ways to go around these limitations at the moment. And to summarize this section, in this section I talked about multimode quasistatic cavity resonance, which enables power delivery efficient with over like 40% efficiency throughout the room, and enables over 50 watts power delivery in accordance with safety guidelines, and while people and like daily objects are present within the volume. And yeah, that's all for this section. As for follow-up work here as well, we're working on other stuff like communicating using wireless power channel. So writing on the wireless power channel to communicate between these nodes and also the node to the room efficiently using a well-known technique called efficient communication technique called load modulation. And we also developed these stuff to extend these work to IoT systems. So that's all I have for this section. And finally, I'm going to conclude this work. So I talked about a 2D wireless charging system that facilitates surface augmentation by using multi-hub wireless power effect. And also, next, I also introduced a 3D wireless power transfer system based on new technology called Multimode quasistatic cavity resonance, and it enables efficient and high power and safe wireless power transfer within large 3D volumes, which is nice. And as for future work, we're still working on refining the system for enhancing system performance, such as efficiency and the orientation dependency I talked about earlier. And also, like, we're working on several wireless power systems, including the one I talked and also the ones I haven't talked about. And these all have pros and cons, so we're looking for ways to integrate them as well. And I'd like to close my talk by acknowledging my awesome collaborators, which work with me on the presenter projects. And now I'm open for questions now. Thank you.
Thank you, Takuya, for the very interesting talk. Dear colleagues, do you have any questions? If yes, please raise your hand. So we have one question from the chat, from the Dennis board. So you can read, or I can just.
Oh, okay, I can answer this question. So the question is, it can be built in any ways. So at the current point, if we're setting the frequencies to 1.2 and 1.3 megahertz, so the receiver needs to be switched between. So that requires one switch, and that's in the current implementation. And probably, yeah, as the question Dennis says, probably making the two modes closer. The quality factor of the room is much higher than the typical receiver, so it might be also possible to like make a receiver that can receive power from both modes. So it depends on the implementation, we're still working. There still needs to be a bit of investigation, but there's a way to solve this. Yeah.
So the second question from the parallel flag, can we call from this charge room?
Well, sure. There's these opening on the corners, and I've made a lot of sometimes I've made Zoom calls from inside of here to demonstrate this technology, and there wasn't any problem. But like that's another part we still need to investigate. So we made an initial evaluation for health effects for human, but we didn't really we couldn't evaluate the interaction between different electronics. So that might be some issue we have to think about. But as a fact, it was possible to do a Zoom call from inside while operating this room. So it should be all right.
Okay, thanks. And we have 4 raised hands. The first question will be from the Mikhail Zubkov.
Oh, yeah. Thank you. I was just wondering if you can scroll back to the images or videos that you had with yourself, I think, maybe, or maybe some of your assistants in the room.
Yeah.
Yeah, but yeah, okay. This is the multi-mode demonstration, right? Yeah. Well, I mean these pictures, because you mentioned that the one of the modes is the pole-dependent mode, but I don't see any pole in the video.
Okay.
Why is that?
So that's because we demonstrated this with the poleless mode. So we are like so we thought we would be good looking as a demo if we looked into pole. And like probably this is a situation that we don't want the pole and demonstrate the capability to do that. So we demonstrated this capability. So driving the room without the pole in this living room demonstration and conducting measurements for. We conducted measurements for both patterns for the demo. We thought this would be more appealing, so we
okay. So it's basically not multi-mode but single mode in the demonstration, right?
Yep, that's right.
Yeah. Okay.
So
okay.
Just
I was just a bit confused. Thank you.
Yeah. Thank you for the question.
The second question will be from Stanislav Glebowski.
Oh, hi. Can you hear me?
Yep, I can hear you.
So first of all, thank you for the very nice talk. It's very inspiring for any electromagnetic researcher working in the field, I believe. And my question is regarding the topology or the realization of your coil for the single element for the two-dimensional system that you created in the first part of the talk.
Two-dimensional?
Yes, no, just the one relay, which is a kind of a honeycomb shaped coil.
Yeah.
So my question is the following. So I can assume that you have a certain distribution of current responsible for coupling to the receiver coil. So you need to maximize this KQ factor in this case. However, you also need to somehow maximize the coupling to the neighboring relays, right? And therefore, maybe some additional turn to some geometry modification may apply to also maximize this power transmission in the case you use a chain of large number of such coil elements. Could you please comment how you solve two these problems simultaneously in your design?
Could I? So, okay, is the question? Is my understanding right? That question is about how this is to tune or like with like these multiple hops and how we made the system not change so much. With
the question is related to the geometry of the coil. So you need a current distribution to maximize both the coupling to the receiver and the coupling to the neighbor. The next relay. In the case you have a chain of such elements. Is it possible to maximize these two couplings, mechanism in the same design?
Oh, the straight answer to that is that we haven't really optimized this structure. We made it work to some extent, and that's what we showed the demo for. And and that's so the efficiency plot I showed later in the slides is a kind of non-optimized result for now. And Yes, and I'm not sure about optimizing both at once. I think we should put priority on the maximizing the KQ factor between these here, because there's more hops here and like more opportunities for losses, and that's how we made the system for now. But like that's gonna be future work.
But if it is not in case it is not a secret, could you please comment? Is it a planar spiral coil inside, or some more sophisticated geometry of a coil?
Okay, well, this is basically a spiral coil here happening. So it's a hexagonal spiral coil, and the reason why we put it hexagonal is because like there will be only adjacent coils. If you put it rectangular, the coupling between the corners. So if you have 4 elements here, the adjacent coupling and also the coupling between diagonal elements will show different values. So that's why we made it a hexagonal kind of coil. And as for secrets, it's on the paper, but like we put capacitors distributed here, so to compensate for the so this is for enhancing Q factor, but like, so if you have one capacitor with a large inductance there, there's going to be a large leakage electric field, and that's going to lead to a large dielectric loss. So we kind of made it splitted. I think this is kind of inspired by like the left-hand rule metamaterials used in your electric field. It's kind of moving back the voltage, so in small chunks, so it doesn't. So to increase the Q factor or decrease the electrical dielectric loss here. So that's probably the only secret we have. Like we put the patterns closer to the edges as possible intuitively because we wanted the coupling between the relay to be strong, and also we wanted a higher inductance because that was easier. That made the engineering easier, and for that we put these capacitors in distributed way to increase inductance, also not getting close to the anti-resonance point of these coils. I might answer your question.
Yeah. Thank you so much for the clarification. It's very nice.
Yeah, thank you so much.
The next question from Agirim Jundalieva.
Hello, can you hear me?
I can hear you, but probably the microphone is a bit small. All right.
Thanks for you nice. Can you hear me? Yes.
Yeah.
Have one question. Have you considered the other resonators designs for use in your work? I tell about your WPT room.
Have I considered different designs? Did you say?
Yes.
Okay.
Why didn't you choose standard resonators?
So in terms of standard resonators, I don't know which part you're talking about. So about coil resonators with my wires, like it didn't show so much extension and range. So that's why we thought making transmitters with surface sheet conductors would make a larger range with higher Q factor and better coupling. And as for, I don't know, if you're talking about stuff like dielectric resonators and those kind of stuff, that's just a different thing for now. We're gonna get to good ceramics to try that out, but I don't. That might work well, but we haven't done comparisons here. But yeah, is that the question? And also for like scaling for these sizes, before I did the room scale thing, I made it a small desktop kind of resonator as well, and that kind of worked in the same principles. So the probably a good point of this approach is, and this might not be related to your question, but like it can get small, and we made the room small and big and work at the same frequencies and and it worked in both ways. So it's also an advantage that we can make these systems in many ways because the lumped capacitors can absorb those geometrical differences. So.
Okay, thank you.
Thank you so much.
So the next question from Minjao Song.
Yeah, can you hear me?
Yep, I can hear you.
Takuya. Yeah. So thank you very much for your interesting talk and the two interesting projects, and also very inspiring results. So I have a question related to the efficiency. So could you please go back to the slide number 58?
Yeah, that's closer. Yeah.
Yeah, so you said the efficiency is about over 37%. So I was wondering about what is the real transmitted power received by the receiver?
Okay, really, so that's kind of arbitrary. So like,
okay, let's talk about the demo, in a demo.
Okay. Demo, so I have it, okay. I forgot, but like, I didn't actually measure the power consumptions of light bulbs and smartphones at that, but like I did that with like a 10-watt inverter or something. So
okay, in that case, what is the input power?
So around 10 watts or something, 10 to 15 watts. So
I mean the input power, so the power sent from the RF amplifier.
Yeah, that's what I'm answering.
That's 10-watt power, and you okay, you can use that
yeah,
power to charge.
Yeah, so one part that I'm not sure about is like I made the smartphone charge, and like this is I checked that the power indicator goes up at least, but like I'm not sure if I really went to the USB qualification, but like so that probably that part concerns you. So like I don't think I actually delivered 5 watts or something, or 2.5 watts to this cell phone at the demonstration in all situations. But yeah, basically these demonstrations were done like with 10 watts or several more watts, and show that they're practical. Like they can like light up a light bulb and run fans, and also make the charging indicator of the smartphone up, and that's what we checked for here. So yeah.
Actually, the efficiency here in this demo is not as high as 40 or 30%.
Yeah, I totally agree with that, because for one reason, because like the receiver is, so in the evaluation in the efficiency here is, first of all, there's 3 reasons. So the first of all is we did the AC to AC efficiency because that's the most fundamental part, like if you want to evaluate a couple resonators. And the second part is that the receiver is, so we did this with a 15-centimeter receiver here. That's like a tablet size or something. And when we did with a 10-centimeter receiver that's closer to a smartphone, we got like 30% or something, same metrics. So that's the second reason. And oh yeah, and for the last one, like this efficiency is when the maximum efficiency of the transmission line from the transmitter to the receiver. So it kind of assumes a perfectly impedance match condition. And in the demo, we kind of did the impedance matching here, but I know, and it was probably not ideal. So that's also a cause of loss. So I agree that in demonstration, we didn't get as much as exactly like 50% or 40% there. But at least
yeah, I understand. I understand. Yeah. The point is, I'm wondering about, so for example, your TX size is more than 5,000 times larger than the receiver size. So what's the coupling coefficient? It should be a very small number. So how can you achieve such an over 30% efficiency, even AC to AC? So it needs a very tough matching, I guess, isn't it?
It needs I'm not sure if like okay I think the thing about low K and the difficulty in coupling should be discussed separately, but like in terms of coupling, I agree that the K should be quite small. I think this kind of made it high efficient because like one, it's the Q factor of the system is quite high, like 1,000 in measured Q. That's not so bad. And also from the coil resonators, probably the field got confined within the volume, so that might have boosted the K as well. But we didn't actually measure the Q, the K in number. Well, that can be calculated from the Q, but.
But how did you calculate this efficiency profile? Well, this is the numerical results, right?
This is the numerical. So yes, this is the numerical results, and we checked that it matches the measure results we got from the S parameters. And yeah, I made a script. As for the numerical results, I just put a script from the simulator directly to MATLAB thing and got this result. So I don't exactly the raw numbers, but at least it matched the S parameter results, the VNA measurement. So I believe it's at least reliable.
Okay. So the last question is from the slide 62 about the SAR evaluation.
Yeah, sure.
Yeah, so you said you used the 50-watt input power to get this image. So is there any receiver in the volume?
Oh yeah, there is a receiver, and so we assumed there was a receiver here that achieved 50% power delivery, 50% efficiency power delivery in simulation environment. So and we did we increased the power level until it hits its SAR limit, and what we got was like around 100 watt input, so 50 watt delivery. We hit the SAR limits in the simulation environment. So that's what this result is saying. Does that answer your question?
Okay. Yeah, thank you very much. Yeah.
So yeah, we still need refinements for this part, but yeah.
Okay, thank you very much. Yeah.
And the last questions from Polina Kapitanova.
Yeah, thank you very much. Very interesting work, and I like your results very much. So may I continue over here? You told that around 50 watt of power can be transferred to the devices in the room. However, it's quite a small value if you take into account that all the objects should be charged. Yeah, for example, TV is not possible to charge with this amount of power. So we can probably charge smartphone, notebook, or laptop. Some couple of fans or something like that. Yeah. So any ideas how to extend this value of the transferred power?
Okay, as like I don't know, like we're kind of a bit in the system engineers and computer science field. So like probably one way is to detect this. So this is and when the human body is close to where the field is intense. So this horizontal axis indicates the human position. These show the different modes. I didn't explain this, but so the 50 watt thing was when it was in the most intense field place. So probably one way to increase this would be to there needs to be more investigation for sure, but like if we can detect where the human is. So suppose like if it's in this area, it can send like a few hundred watts before hitting the safety guidelines. And I don't know if we should actually go to the limit there, but like at least we can deliver more power if we know where the human is. And yeah, that's one possible way we're
Okay, thank you. And one more question regarding the frequencies of operation. You have chosen the operational frequency of about 1.2 mega or something like that, yeah? However, we know that there are some standards like G standard or also ASM band at 6 mega are normally used for the various power transfer applications. So didn't you try to optimize your room for G standards, which operates at 200 kilohertz approximately? It will be compatible to the electronic devices which are in our pockets at the moment, you see?
I strongly agree.
What is the general limitation? Yeah. If there are any general limitation for this optimization or not?
As for lower frequencies like Qi,
to the lower
probably it's going to be harder because it's going to be hard to maintain a high Q factor with those frequency bands. And as a scientific paper, we thought we should get higher efficiency because that's what most people care about. And yeah, we haven't actually done an analysis, but I suppose tuning these to Qi frequencies would work at some degree, but also make a degradation, decay the performance as well. That's does that answer you? So yeah, that's future work.
Yeah, that's enough. Yeah, and probably the final question for me. So what is the outlook? Are you going to sell these rooms as a product? So probably in next 10 years, everyone will have this room and will live in such a room. And so is it the goal or not? Do you see this room in the future as a product?
Well, in the far future, yes, but like probably it's not going to be a few year thing. Like I know you've been doing a lot of wireless power transfer projects, and you know it's hard to commercialize these stuff. So we started with the room because that's the most appealing application for like, and we can talk about a few 10 later stuff in scientific papers for inspiring people. But probably the most starting application is going to be for stuff like, I don't know, like powering sensors inside mouses in like experimental setups. So they can also, this can also be small or big or in any frequency. So that's probably one closer way to commercialize or make these work in practice. So yeah, your point is right. So
okay, thank you so much.
Room.
Thank you.
Thank you very much. Dear colleagues, do you have any other questions? So if not, I'd like to thank the speaker again. Very interesting talk. So, and we are moving on. We need to finish. So thank you very much for being here. And the next seminar will be next Monday at 4 p.m. Where our PhD student Victor Puchin will be talking about his research in MRI. So thank you very much again, and see you everybody next Monday. Goodbye.
Thank you so much for inviting me. Great discussion.
Thank you. Thank you for coming. It was really nice to hear you. Bye-bye.
Thank you. See you.